In this video, we're going to see the difference between ideal diode and practical diode. This equation is called ideal diode current equation. In the previous video, we derived this equation by making a bunch of assumptions. If a diode IV characteristics match this diode current equation, we say that diode is ideal diode. But then, why wouldn't a practical diode meet this ideal diode current equation? In order to understand that, we need to go through all the assumptions that we made one by one and see why each assumption cannot be met by a practical diode. First assumption being the depletion approximation, where we assumed the PN junction has only depletion region and neutral region. But in practical diode, we actually have depletion region, partial depletion region, and neutral region. If you take volume charge distribution across the PN junction, this is how the graph looks like. We have seen this before, where we assume this is P plus and this is N. And if we understand what is depletion, basically this is the depletion region, and we have a partial depletion region here, and this is neutral region. And similarly on P plus side, we have depletion region, partial depletion region, and neutral region. So based on depletion approximation, we are assuming that this region is basically 0. But in reality, this won't be 0 exactly. It will be a finite distance. But if you see, the percentage of this partial depletion region is higher in a low doped site, whereas it is very less on high doped site. So if we can assume a highly doped PN junction where both sides are highly doped, then doing this depletion approximation would be very close to a highly doped PN junction. For a highly doped PN junction, we can say partial depletion region would be very close to 0, which means a highly doped PN junction diode can be very close to an ideal diode in terms of this approximation. Moving on to the second assumption, where we assumed all the potential applied across a PN junction diode is directly getting applied across the depletion region itself. But in practical diode, the potential that we apply across the PN junction should be equal to the potential that gets dropped at the metal semiconductor junction, which we assumed is ohmic in nature, and we can say some potential gets dropped across the contact. So we have two contacts, so I'm taking 2 times the contact potential drop, plus there would be potential drop across P region. So I'm taking that potential is Vp, and there would be some potential drop across the N region. So that is Vn plus the potential that gets dropped across the depletion region, Vd prime. Now in fact, in our ideal diode current equation derivation, we assumed that all these components are basically 0. So that Vd prime is Vd, and we can directly substitute that Vd here. Let's say in practical diode construction, we choose the metal in such a way that potential drop at this contact is very less so that we can neglect. So let me say even in practical diode, we can make it very close to 0. But then how about this potential drop on P side and N side? Because neutral regions length would be finite and there is a cross-sectional area. If you know the resistivity on N side, we can find what is Rn, which is rho n times L over A. This resistance cannot be neglected. And similarly for Rp, the resistance on P side. When current is flowing, there would be finite potential drop on the neutral regions of P and N. We literally assumed this value is 0. But then, when can we assume at least this is not 0, but at least a very small value, is when the doping on both P side and N side is really high. Then the resistivity would be very small. As a result, resistance and potential drop. Then we can say a highly doped PN junction is very close but not exactly equal to an ideal diode. Coming to the third assumption, under thermal equilibrium, we had an equation which said Pn naught, the minority carrier concentration on N side, is related to majority carrier concentration on P side by this equation. This is called junction law, which relates the carrier concentrations of same type on either side of the junction by the potential across the depletion region. And we extended this and said, even when the diode is not under thermal equilibrium, that this equation would be valid, telling Pn would be equal to Pp times e power minus of Vbi minus Vd over Vt, whereas Vd is the potential across the depletion region. But in fact here we didn't know either of the quantities Pn and Pp. So we made another assumption. This is very close and linked to this third assumption. To understand this fourth assumption, let me take the minority carrier concentration distribution in the PN junction diode. So this is how it looks, where yellow curve represents the whole concentration distribution on N side, and the red curve indicates the electron concentration distribution on P side. Because of the applied potential, excess holes were injected onto the N side, and this excess hole concentration right at the edge of the depletion region is, let's say, del P, assuming that del P is far less compared to the thermal equilibrium carrier concentration on N side. And similarly, we can say this del N is very small compared to the P naught. And this assumption is called low-level injection assumption. As del P is small, the electron concentration reduction to recombine these excess holes at the edge of depletion region would be very, very negligible. We can say right at the junction edge, Np would be Np naught. And similarly on P side, Pn at x equal to minus xp would be Pp naught. Based on this assumption, we can rewrite Pn is equal to Pn naught times e power Vd over Vt. So we can say this value would be Pn naught times e power Vd over Vt, and in the same lines we can write this is Np naught times e power Vd over Vt. As N side is lightly doped compared to P side, as P is P plus, Np naught would be less compared to Pn naught. As a result, this del N is small compared to del P. And now coming back to for what kind of diode these assumptions would be close to being valid. Nn naught is actually the doping concentration on N side, and Pp naught is doping concentration on P side. If Nd and Na are very high, so does Nn naught and Pp naught. Then this assumption would be really valid. We can say, based on these two assumptions, if a PN junction is highly doped on both sides P and N, then that diode would be very close to satisfying these two assumptions. And now the last assumption, no generation and recombination in depletion region. We know if doping Nd and Na are small, depletion width would be large. When depletion width is large, the probability of generation and recombination in a practical diode would be high. Let's say if W is considerable to the diffusion lengths of holes and electrons, then definitely we cannot neglect the generation and recombination in the depletion region. But then when can we neglect so that this approximation would be valid is when Nd and Na are very high, then depletion width would be very, very small. Then we can say the generation and recombination that happens in that small depletion region can be neglected. So again, we can say a highly doped PN junction would be close to this fifth approximation. And based on this fourth assumption, under low level injection, the current flowing would be small. When current flowing is small and resistance is also small, the voltage drops on P side and N side can be neglected. So bottom line, out of all this discussion, a highly doped PN junction diode would be very close to satisfying this ideal diode current equation. And another point to note that reverse saturation current I naught is given by this expression, where Pn naught is the minority carrier concentration on N side and Np naught is the minority carrier concentration on P side. And if doping on both sides is high, then minority carrier concentrations would be small. Then I naught would be really small. Having high doping reduces even the reverse saturation current. The last point before we close this topic, The ideal diode current equation is given here. If you plot it, it would look like this. For practical diodes, the curve would look something like this, where the equation can be modeled mathematically by introducing a parameter called eta. Because we know that Vd is not the voltage that directly gets applied across the depletion region, based on which we actually derived the diode current equation. As the applied voltage doesn't directly get applied across the depletion region, and because of other assumptions not getting satisfied, we can simply represent a parameter called eta, where Vd over eta would be less than the voltage that you actually apply across the diode, which means Vd over eta would be less than Vd. So which means that eta should be greater than 1. For an ideal diode, where in this case eta would be equal to 1.